All right, in today's session, we're going to be looking at stoichiometry. So stoichiometry just refers to the quantitative relationship between the relative quantities of certain reagents, or in other words, the numeric relationship between the relative amounts of certain substances. And notice that I use reagents and substances interchangeably. Reagents refers to both products and reactants. Reagents don't necessarily have to be reactants themselves. There are three different types of stoichiometric conversions. We have mole to mole, where you have the number of moles of some substance A, and you're trying to figure out the number of moles of some substance B. And this sort of process only takes one step. It requires you to look at the balanced equation. That's it. The second type of stoichiometric conversion is moles to mass, volume, or number of molecules, and it can go the other way around as well. So you can have the mass, volume, or number of molecules, and you can also be finding the number of moles. So in this one, you're just using either the periodic table if you're trying to figure out the mass, or you're trying to use the fact that there are 22.4 liters per every mole at standard temperature and pressure, which is what STP stands for. Or you're going to be using Avogadro's number, which is 6.022 times 10 to the 23rd. It's a huge number. It makes the number of grains of sand on Earth just seem puny in comparison. But that number pretty much tells you that's the size of a mole. Anyway, we would be using any of those methods to figure out either the mass, volume, or number of molecules of one substance given the number of moles of another substance, or maybe you would be using it the exact opposite way. So you're given the mass, volume, or number of molecules, and you're trying to figure out the number of moles of another substance. And the third case, which takes 3 steps. So moles to molecules just takes 2 steps. So this last one takes 3 steps. And that's when you're trying to get from mass, volume, or number of molecules of one substance, and you're trying to get to the mass, volume, or number of molecules of the next substance. So in order to solve for these kind of problems, we need to use a method called dimension analysis, and that's what we're going to be looking at in just a little bit. So for our first example, we're going to be using silver nitrate and barium chloride. So in this problem, silver nitrate reacts with barium chloride in order to form silver chloride and barium nitrate. So the first thing that you always want to be trying to do is just write out the balanced equation. So let's try balancing this out. You have silver nitrate, AgNO3, which is reacting with barium chloride, and it forms AgCl and barium nitrate. So a thing that you always want to be noticing in order to balancing out a chemical reaction is the number of each type of element. So in this case, we have for each type of molecule at least. So in this case, we have Ag, which is silver. We have one of them on this side, and we have one Ag on this side as well. We have one barium on both sides. We have two chlorides, 2 chlorine molecules on this side, while we only have one chlorine molecule on this side, and we have one nitrate on this side, notice I used the entire molecule of nitrate instead of separating it out into nitrogen and 3 oxygens. You could do that as well, but it's very simple if you just use pretty much parentheses and try to group it together. But we have 2 nitrates on the other side. So we want to make sure that the total number of each element is going to be the same on both sides. But we already have a differing amount of nitrates. So in order to fix that, we can just multiply the first reactant by 2, which gets us 2 nitrates and 2 silvers on one side. And in order to balance out the 2 silvers, we can multiply the AgCl by 2, which would get us 2 Ags on both sides. And it would also get us 2 chlorines on both sides. And this leaves us with a balance in the silvers, a balance in the baryons, a balance in the chlorines, and a balance in the nitrates. All right, now that we have our balanced out chemical reaction, we can go on with using dimensional analysis in order to solve for the number of moles of silver chloride given the number of moles of silver nitrate. So notice it gives us the number of moles of silver nitrate, and it says there's an excess amount of barium chloride, which means that we really don't need to look at, we can simply ignore the number of moles of barium chloride completely. Right, let's start with the dimensional analysis table. So dimensional analysis just refers to trying to make a proportional relationship between all these different factors. So we're given 8.41 moles of silver nitrate, AgNO3, and we know that for every 2 moles of AgNO3, there are 2 new moles of AgCl, or silver chloride, that gets formed. And just based off of this, we can cancel out the units on both sides that are getting divided out, and we cancel out the moles of silver nitrate with one another, and we're left with only the moles of silver chloride, which leaves us to say, and here we just need to multiply out whatever is on the numerator and divide out whatever is on the denominator. So this is going to be 8.41 times 2 divided by 2. I mean, times 2 and divided by 2 cancel each other out. So we're left with 8.41 moles of silver chloride that gets formed. All right, so in our next problem, we have nitrogen gas, which is reacting with hydrogen gas, which forms nitrogen trihydride. So again, let's just start off with the balanced chemical reaction. So we have nitrogen gas, which is going to be N2, added with hydrogen gas, which is H2. Remember, both of these are diatomic molecules. And it yields nitrogen trihydride, NH3. Tri means 3. Right, so we have 2 nitrogens on one side, while we only have 1 nitrogen on this side. So in order to balance that out, we can just multiply by 2, which yields us with 6 hydrogens on this side. And we only have 2 on this side. So in order to cancel that out, we can just multiply by 3. And now we have 6 hydrogens on both sides. All right, now on to the question. Now we're trying to figure out, this is a type 2 kind of stoichiometric problem. We're trying to figure out the number of grams, the amount of grams of nitrogen gas, which is needed to react with 1.03 moles of hydrogen gas. So again, we are starting off with 1.03 moles of H2. And using the balanced equation, we can say that for every 3 moles of H2 that's getting consumed, 1 mole of N2 is getting consumed. And now there's one more step, which is that every mole, so moles of hydrogen gas cancel each other out, and every mole of N2, periodic table, we have nitrogen gas with a molar mass of 14.007 grams, but that would only give us the mass of nitrogen, only one nitrogen, one atom of nitrogen, but 1 mole of one nitrogen. But in this case, we're using N2, which means that we would need to be multiplying that amount by 2. So we would have 28.01 grams of N2. Now we just cancel out the moles of N2 and we would be left with just grams of N2, which is exactly what we're trying to be finding out. So we would just be multiplying 1.03 times 28.01 and dividing it by 3. And that would get us 9.62 grams of nitrogen gas, diatomic nitrogen gas. All right, in this next problem, we have the combustion of octane. And combustion refers to fire, creating fire or explosion. And it always involves some sort of carbon-based molecule and oxygen. So combustion of octane, oct for 8. You probably don't need to memorize this, but it is C8H18. It's a hydrocarbon. And combustion of octane, so we're always combusting with oxygen gas. And that's going to combustion always yields carbon dioxide and water. At times you're going to see carbon monoxide as well, but in most cases you're only going to be looking at carbon dioxide and water. So now we just need to balance out this equation. So on one side we have 8 carbons, 1 carbon, 18 hydrogens, and 2 oxygens. On the other side we have 2 hydrogens and 3 oxygens. In order to balance out the hydrogens, it may seem like we just multiply by 9, which would get us 18 hydrogens, which is the same amount. However, you're going to notice that whenever you multiply by 9, we would also get 9 oxygens, which means on this side we would have an odd number of oxygens. There's an even number here, and no matter what number you multiply an even number of oxygens by, you're going to get an even number and odd number here. So when you add an odd and even number, you're going to get an odd number. On this side, we are always going to get an even number. So in order to avoid that, we would need to be multiplying it by another factor of 2. So instead of multiplying it by just 9, we would be multiplying it by 18, which would give us 36 hydrogens. And instead of 3 oxygens, we're going to be getting 18 oxygens. And so now we have, so to balance out the 36 hydrogens, we're going to need to multiply the number of carbons by 2, or the number of octanes by 2, which would give us 36 hydrogens balanced out. And this would give us a new number of carbons as well. It's going to give us 16 carbons. and we only have one carbon on the other side. To balance out that, we could just multiply by 16. We have 16 carbons on both sides, 16 hydrogens on both sides. And now just to balance out the number of oxygens, we have 18 plus 16 times 2, which is 50 oxygens. And in order to get 50 oxygens on the left side, you can just multiply O2 by 25, which would give us 50 oxygens. And now we have a completely balanced equation. Since we're given two different reactants, we need to figure out which is the limiting reagent and which is the one that's in excess. In order to find the limiting reagent, we can utilize dimensional analysis once again by trying to figure out how many moles is 6.97 times 10 to the 24 molecules of octane. So to do that, we have every mole of octane is made out of Avogadro's number, 6.22 times 10 to the 23 molecules of C8H18, and both of these units cancel each other out, and that's how much you see in 1 mole of C8H18. And when we multiply this, we get the number of moles of octanes that we used, which is equal to 11.58 moles. C8H18. Now for the number of moles of oxygen gas that we used, we have 37.4 liters of oxygen gas, and we know that for every mole of oxygen gas at standard STP, we would be getting 22.4 liters of O2. And liters O2 cancel each other out, and now we're left with 1.67 moles of O2 gas. So just by looking at this, we can already tell that oxygen is going to be the limiting reagent, because for every 2 moles of octane, you need 25 moles of oxygen, and if you only have 1.67 moles of oxygen, that means we definitely cannot completely react 11.58 moles of octane. We use 1.67 moles of oxygen gas as a limiting reagent, and we use that for the rest of our calculations. We have 1.67 moles of O2, and for every 25 moles of O2 that is reacted, we get 16 moles of CO2. And using the periodic table, we know that carbon weighs 12.011 grams, and each oxygen weighs about 16.0 grams. So 16 times 2, that's 32, plus another 12, that's about 44 grams for every mole of carbon dioxide. So we have 44.01 grams, to be exact, of CO2 for every 1 mole of CO2. And now we're just canceling out the units. You're left with 1.67 times 16 times 44.01 divided by 25, which leaves us with about 47.5 0.03 grams of CO2. So just over 1 mole of CO2 gas is formed in this reaction. That's all there is to stoichiometry. I mean, it's all just utilizing dimensional analysis to figure out the number of grams of the number of grams or whatever quantity it is that you're looking for given some other quantity of another reagent.